This is Sarah Wilkinson from Humber College and the University of Guelph-Humber. This video will cover why the respiratory exchange ratio does not always equal the respiratory quotient, and this occurs during non-steady state conditions. You'll want to watch previous videos that covers what is the respiratory exchange ratio and what it can tell us about fuel use, and the basis for determining RER and how RER is equivalent to respiratory quotient during steady state conditions. This video will cover RER as it pertains to non-steady state conditions. As a quick review, last video we covered that the respiratory exchange ratio, which is measured at the mouth, is approximately the same as the respiratory quotient measured at the tissues. That is, the carbon dioxide produced divided by the oxygen produced at the tissues can be measured at the mouth. However, during non-steady state conditions, RER no longer equals RQ. And this happens when people hyperventilate or during exercise past the ventilatory threshold. So let's start with exercise past the ventilatory threshold. The ventilatory threshold is the point where pulmonary ventilation increases disproportionately with oxygen consumption. So on this graph here, you can see that here we have minute ventilation, the volume of air taken into the lungs per minute. And on the y-axis we have VO2, so how much oxygen is being consumed to produce ATP. Minute ventilation increases linearly until ventilatory threshold, where VO2 continues to increase. However, there's an exponential increase in minute ventilation. This exponential increase in minute ventilation is entirely due to an exponential increase in breathing frequency, so how frequently you breathe per minute. And this is stimulated by the sympathetic nervous system for a number of reasons, which I won't cover here in this video. What this does to RER is it artificially increases the carbon dioxide measured. So with a greater breathing frequency, the metabolic cart is going to measure a higher production of carbon dioxide as compared to oxygen consumed. VO2 at the mouth is a pretty accurate reflection of what's going on at the tissue because the majority of oxygen is carried by hemoglobin. However, VCO2 at the mouth is not necessarily an accurate reflection of what's going on in the tissue because of the way carbon dioxide is carried in the blood. So you've probably covered how carbon dioxide is carried in the blood. The majority, 70% approximately, is carried in the form of a bicarbonate ion. So just as a quick overview, this here is a blood vessel, and carbon dioxide produced in the tissues ends up in the red blood cell where it combines with water in the presence of an enzyme, carbonic anhydrase, to form carbonic acid. Carbonic acid dissociates to hydrogen and the bicarbonate ion, which then leaves the red blood cell and travels as bicarbonate in the plasma to the lungs. Now, we have quite a bit of bicarbonate dissolved in our blood at all times. So it's not just carbon dioxide produced at the tissue that results in bicarbonate in the blood. There's also a baseline amount. What happens when we breathe very frequently, so when we start to hyperventilate, this bicarbonate naturally dissolved in our plasma ends up being reconverted to carbonic acid and reforms carbon dioxide. The reason for this is with greater breathing frequency, more carbon dioxide is leaving the blood. So the bottom line is, can RQ really go above 1? And the answer is absolutely not. So RQ, VCO2 divided by VO2 at the tissue does not go above 1. And so let's have a look at some real data. So this is data from a VO2 max test I did on a participant, and you can see that what we did is over time we increased the workload so that VO2 goes up over time. And here we can see that RER starts off at 0.8, and as exercise intensity goes up, it goes up as well. And what you can see at a particular point, RER measured at the mouth goes above 1. And so what is actually going on at the tissue? So let's look at what we can use RER for. As you can recall from a previous video, if we look at RQ, it actually helps us predict the percent carbohydrate and percent fat. So let's look a little bit closer, and you can see here that an RQ of 1.0 means that the person is using 100% carbohydrate to produce ATP. RQ 1.0, what does this mean in terms of RER if it's above 1? Well, recall, we can't use more than 100% carbohydrate. Impossible. So what does this data really mean? So here's our RER of 1, which means an RQ of 1. RER of 1.07, what does this mean in terms of RQ? It means at the muscle, RQ is still 1. RER of 1.12, RQ, 1. RER of 1.15, RQ, 1. So here you can see that during non-steady state condition, when this participant has passed their ventilatory threshold, RER no longer accurately reflects RQ. So we've just talked about exercise past the ventilatory threshold. We can expect RER to go above 1. Let's just briefly discuss how hyperventilation can affect this, especially at rest. So let's take a typical exercise test in the lab, and you can see this participant has quite a few people surrounding him. He has a face mask. And, think about your own situation. Anytime there's a test, you have sympathetic nervous system activity, and this is going to potentially affect your breathing rate. So this might artificially increase breathing frequency. You might also look at the folks around him, and that this also might affect the way he breathes. In addition, the face masks and the nose plugs and the whole getup that you put on participants is a little awkward. And so what you'll often see is that at the onset of the test, the first RER measurements may be artificially high. And then over time, you'll see that as the participant becomes familiarized, RER will approximate what you would expect. So when I often put a face mask or nose plug or whatever on someone, we'll see RERs of 0.85, 0.9. I know that they're probably not actually that. So the RQ is probably not 0.85, 0.9. And that over time, as the person just sits on the bike and becomes accustomed to breathing into the face mask and the nose plug, that their RER will actually start to go down. And again, what's happening here is the bicarbonate in the plasma, as the person breathes more frequently, they'll actually artificially blow off more carbon dioxide. They're not actually producing more, they're just blowing off more. So to summarize, during steady state conditions, RER measured at the mouth is approximately the same as what's going on at the tissues, with a bit of a time delay. However, during non-steady state conditions, RER no longer equals RQ. And these would include hyperventilation at rest, as well as exercise past the ventilatory threshold.